All right, let's really unpack this one. Welcome to the deep dive. We take complex topics and, well, try to give you a shortcut to really understanding them. Today, we're diving into something pretty fundamental in physics and engineering, the Carnot cycle.
That's right. And our mission, you could say, for this deep dive is to explore this theoretical framework. It was proposed by Sadi Carnot. It really defines the absolute limits of converting heat into actual work and, why it's still so important even though it's, well, purely idealized. We're drawing our insights from various Wikipedia sources on the cycle itself, the Carnot heat engine, and Carnot's theorem.
Okay, so 1824, we have this French physicist, Sadi Carnot, and he dreams up this ideal thermodynamic cycle. It's like a thought experiment, isn't it? The perfect engine, setting the absolute ceiling for how efficiently any engine can turn heat into useful work. And later on, others like Clapeyron and Clausius, they built on it, gave a more mathematical backbone.
Exactly. And what's really elegant about it is its simplicity, in a way. It describes an engine that just operates between two temperatures. You've got a hot reservoir at TH and a cold one at TC. Simple as that. The engine takes in some heat, QH, from the hot side,
Right.
dumps some waste heat, QC, into the cold side,
Okay.
and the difference. That's your useful work, W. But the absolute key feature, the sort of magic ingredient, is that the whole cycle is perfectly reversible.
Reversible, meaning like no friction, no losses at all.
Precisely. Every step could theoretically run backwards without any energy dissipation or increase in entropy. It's this ideal frictionless nature that lets it hit that maximum possible efficiency.
So let's walk through it. Imagine some gas, maybe, inside this perfect engine. 4 steps, right? First, isothermal expansion.
Right.
It grabs heat from the hot reservoir, expands slowly, does work, but keeps the temperature constant at TH, like a gentle energy release.
Exactly. Perfectly controlled.
Then, stage 2 is adiabatic expansion. It keeps expanding, doing more work, but now it cools down, and crucially, it's totally insulated. No heat gets in or out.
That's the one. Perfectly insulated during that phase.
Okay, then step 3, isothermal compression. Now we're putting work into the gas, squeezing it, but keeping it at the low temperature TC, and it pushes heat out to the cold reservoir.
Yes, actively rejecting that waste heat.
And finally, adiabatic compression. More work goes in, squeezing it more, heating it back up to TH, again, completely insulated, no heat exchange.
And if you draw this on a pressure volume graph, which is the classic way to visualize it,
Right, I've seen those diagrams.
the area inside those 4 curves, that loop, that area, is the maximum work done by this ideal engine per cycle.
So, okay, we've got this perfect theoretical cycle. But the big question, the one engineers always ask, is what is that ultimate efficiency limit? How good can it possibly get?
Ah, yes. And that brings us to Carnot's theorem. It formally states it. No engine, absolutely no engine working between those same 2 temperatures, TH and TC, can possibly be more efficient than this ideal Carnot engine. And the formula for that maximum efficiency, eta, is surprisingly simple. Eta equals 1 minus TC divided by TH.
1 minus TC over TH.
Okay. What's really interesting there, maybe a bit counterintuitive, is the impact of those temperatures. Lowering TC, the cold sink temperature, actually boosts that maximum theoretical efficiency more than raising TH, the hot source temperature, by the same amount.
Really? So getting colder is more effective than getting hotter, in a sense.
For efficiency gains, yes. It puts a lot of focus on how effectively you can reject that waste heat. It's a key insight for practical design, even if the Carnot cycle itself isn't practical.
Which brings us to the obvious question.
Yeah.
If it's the best possible, why aren't our cars and power plants running on Carnot cycles?
Well, Carnot himself knew it was just theoretical. You can't actually build it. Real engines, you see, they always have irreversibilities. Friction, heat leaks, they lose energy. So, real engine efficiency, Italiali, is always less than the Carnot efficiency.
It was less.
Always. To build a true Carnot engine, you'd need things like, well, infinitely slow processes for heat transfer, perfect insulation, 0 friction, conditions you just can't achieve in the real world. It takes infinite time, basically.
So it's a benchmark then, a theoretical ideal we can't reach.
Exactly. It's an incredibly valuable model, even if it's unbuildable. Think about Rudolf Diesel. He was apparently deeply inspired by Carnot's ideas. He was chasing higher efficiency, trying to get closer to that ideal, maybe trying to approximate that isothermal heat addition.
And that led to the diesel engine.
Directly. His work, driven by trying to approach these theoretical limits, even if he couldn't perfectly achieve them, led to the modern diesel engine, which was, a huge leap in efficiency compared to earlier engines. The Carnot cycle is like the North Star for engine designers. It tells you the absolute maximum possible, the theoretical limit you're always striving towards, even if you know you can never quite touch it.
So wrapping this up then, if you had to give our listeners one core takeaway from this dive into the Carnot cycle, what would it be?
I think it's that nature has fundamental rules about energy conversion. Even with perfect engineering, there are hard limits on how much useful work we can squeeze out of heat. Understanding that limit, the Carnot limit, it doesn't just guide engineers trying to make better heat engines. It also pushes us to think differently. It inspires exploration into completely different ways to get work from energy, like, say, fuel cells. They convert chemical energy directly, you see, so they aren't bound by these same thermal bottleneck rules. It just makes you appreciate the elegant constraints of the universe and how we innovate within them. Keep pondering those rules.